In this presentation, I try to explain you the new PubSub technology that's defined in OPC UA. And I actually want to start with going quickly through the client-server communication model that is the basis of OPC UA and is still the thing that is used. The publisher-subscriber model was defined in OPC UA 104, which came out almost 4 years ago, but we still haven't seen that very much in real life. But we have some uses for it already established, but I still see that it's more like an upcoming alternative model. So I explain how the model goes and how it compares to the client-server model. Then I'm giving out a few scenarios where the PubSub model is useful and improves what we have today. And at the end of the presentation, I show you 3 demos that we've been working on at Prosys OPC. So if we look at the client-server model, it's based on the idea that we always have 2 components. The other one is a server, and the other one is a client. The client is the active component that connects to the server. And I'm using here a little bit on the side screenshots from our demo applications and test applications, OPC UA browser and simulation server, which are free applications for everybody to use to try out and test all kinds of connections. Unfortunately, they don't support PubSub yet, but they have very good support for the client-server communication. And the same principle works with any applications in the market. So in the client-server model, the client is always first making a connection, which includes creating a session. And the session also defines the security context for the whole communication that's going on after that. Once the session is created and activated, the client can browse the address space of the server to find out what is available from the server, what data is available, and what kind of metadata is available. After that, the client can read variable values typically, but also the metadata that is defined in other attributes of the variables and other nodes that are in the address space, and also all the type information that is there behind the objects in the OPC UA server. And all the information modeling is basically based on defining these types and standard types, and then the instances, the objects, they follow these types. And by browsing the address space and reading that information, you can read the information models out of the servers. The client-server model also enables writing variable values most often, and in theory you can also write metadata, but that depends on how the servers actually enable that. The client can also call methods if the server provides them, and this was already mentioned in the previous presentations, that is a very useful model for modifying or controlling the server or changing the state of the server and things like that. The client-server model also defines how to read history if the server makes it available. And there can be history for variables and events. And one final thing that the client can do when it is finished with its communication, it disconnects, and part of that is closing the session that was opened in the beginning. So this is basically the client-server model and all the services that are in there. Plus, there are also subscriptions. And the subscriptions are used for monitoring changes in the server. And the model works on the principle that the client creates a subscription for itself in the server. And then it creates monitor items in this subscription that define variables to monitor or event notifiers to monitor. And after that, the client starts calling the publish service in the server. And as a result, it gets notification messages from the server that include data changes for the variables and events. And this is a subscription model, and it's also already using these terms publish and subscribe, but it's part of the client-server model. The main scenario for the client-server model is this typical supervisory control and data acquisition, whereas data application acts as a client towards PLCs or sensors or different devices. But there can be also applications on top of the SCADA, like MES, that also makes a client-server connection to the SCADA, or a historian that is monitoring changes in the SCADA application. But even the PLCs can communicate with each other as is defined in the PLC Open information model. And this is already established today, and these are the main scenarios where OPC UA is used. The client-server model scales. We can have more clients, but every client makes and creates its own subscriptions in the server. So the more clients, the more subscriptions the server has to take care of and keep up to date. There can also be more servers in the network, and then the clients can connect to each of these. And eventually the question is that how many connections can we really handle in practice? So the pros and cons of the client-server model are that there is a session always open. It's good in the sense that we have a security context between that session. But on the other hand, it requires a steady connection that suffers from network interruptions. And also it requires resources for each connection, so it doesn't scale limitless. There are also client-specific subscriptions. So the good thing is that every client can order whatever it wants from the server. But on the other hand, it also requires resources for each connection for each client, and again doesn't scale that well. The client-server model also has these synchronous services like reading history, writing, calling methods. And it can provide the information models as I described from the type part of the address space, and this is discoverable for the client applications. Security is flexible, and you can have fine-grained rules per application and user who can do what in the server, who can access what information, and so on. Okay, so next part, the publisher subscriber model. How does it differ? The idea here is that we start talking about different components. We talk about the publisher. And in the publisher model, you can create data sets with variables or event notifiers. And then the publisher can just start publishing these datasets through dataset messages to the network. And the dataset message can contain data changes and events. So this, in fact, looks pretty similar to the subscription model in the client-server version, that we are publishing similar data, but in a little bit different manner. And now you can have a subscriber, or actually any number of subscribers, that can then filter out information that is published into the network. But the subscribers don't basically define what is published in the network. So that's the difference. This model scales. We can have basically any number of publishers, any number of subscribers, and they are not all of them connected to each other, but instead they just connected to the same network. So this is highly scalable. And we have a customer that has verified a scenario where they have 2 publishers and 31 subscribers in the same network. They're sending 40,000 complex variables to the network from 2 publishers, both of them 3.5 megabytes per second. And they managed to establish this scenario only with the publisher subscriber model. They were struggling with the client server model with this amount of data. The publisher subscriber is based on networks, as mentioned, and we have 2 types of networks. We have local networks, where we can use UDP broadcast messages, or as Georg mentioned, there will be the new Ethernet advanced physical layer coming up using like more raw layer of the Ethernet. And this will be used very much in the new field exchange, I think, in future. And in this model, the OPC UA specification defines a binary UADP, UA datagram package messages that are very optimized, and you should get the best performance together with the best performance of the network, so that you can really broadcast huge amount of data if you need to. And as Georg mentioned, with TSN, this network can also extend to real-time capabilities for deterministic capabilities, but that comes like automatically from the network. So in this level, we're just using UDP or Ethernet APL for the messaging. The second alternative is that we can use the same model with message queue brokers, which most commonly are Mqtt brokers, but there is an alternative, the AMQP. And in these cases, the messages are typically JSON messages, which are more like textual messages, but there is an alternative to use UADP if you need more performance. The security is a little bit tricky, especially in the local network. You need basically an external security key server, because the subscribers and publishers have to share some keys with each other. But then you can encrypt the traffic in the network. And the idea is that both the publisher and subscriber will get the common key for the encryption from this security key server, and then they can encrypt and decrypt messages. But it's not so easy to like provide data for only certain subscriber or so on. It all depends on the configuration in the security key server then. On the message queue broker side, it's actually easier to provide security because you can use SSL, and with the SSL security, you can do both encryption and also user-based authentication to the broker. So there are some pros and cons in the publisher-subscriber model, that now we don't have the sessions, which is good, that we don't need the connection management. Doesn't matter if the connection is not on all the time. It's flexible at unreliable networks especially. but it requires this external shared security key server with UDP or Ethernet APL. It's multicast, so you can deliver big amounts of data to many receivers. It's using fixed data sets, which means that on the publisher side, you have fixed resource management, and this scales to large networks, but on the other hand, it's using a static configuration. There are no synchronous services, and the configuration, especially in large networks, can get quite complicated, and it's still a bit of an open question. So let's look at the scenarios where this model can have some improvements. So the old world, the industry 3.0, is basically this automation pyramid, and the client-server model works very well here when we have this hierarchy-based communication. But now the world is moving towards industry 4.0, where everything is connected, and the publisher-subscriber model should provide better capabilities for communication among all participants, and that's where we hope to be able to use this more. Basically, you can start by improving existing client-server applications, so you don't need to use publisher-subscriber on its own. It's more useful when you combine it with the client-server model. So you could just have a publisher server that is both a server and a publisher. You can also have a subscriber client that is both a subscriber and client. And the client can use the synchronous services to the server to read, write, get the information models, and then start monitoring data from the publisher instead of using the traditional client-server subscriptions. You could also, of course, have a publisher client that is using client-server connection to the server and then publishing data, or a subscriber server, or a component that can do all four of these, and then you are totally free to combine it. The main scenario is synchronizing servers with each other. So especially in the local network, we could have traditionally 2 OPC UA servers. They could be hardware devices, and by adding publisher subscriber functionality to those, we can make them both publish their level information, for example, to the network. Both have their own levels, but then they can subscribe to each other's levels and add that information to their address space and use that also for real-time control, for example. Another common scenario using the broker idea is from going to edge to cloud, and then the edge server would get a publisher component and use the Mqtt broker to publish JSON messages that are subscribed in the cloud. And here we have just one-way data delivery. And typically you can use then the so-called non-reversible JSON encoding so that the subscriber that is in the cloud doesn't need to know anything about OPC UA in practice. And you can have a secure JSON, secure Mqtt connection using SSL on top of Mqtt, providing encryption and user authentication to the broker. So that's the scenarios, and now we have tried it out in a few demos. I have 3 demonstrations to show. The first one is the Azure demo that we have published in our blog already. So here we have added a publisher, or used actually our sample publisher server that comes within our SDK for Java. So you can also try that out yourself. And with the certain parameters, we can have a secure connection to Azure. So if you provide an SSL address, you have an SSL encrypted connection, and with the username password parameters, you can authenticate to Azure. And in Azure, you typically get these from the IoT Hub, these parameters. And we're using the non-reversible JSON that I mentioned. And in that case, the dataset message that is being sent is very simple. So it's just a list of an array of variable names and values and their timestamps. And then it's easy to process this in Azure without any special knowledge about OPC UA. The next demo that we'll be working on, well, we haven't published this yet, but we checked it out, is kind of the same thing with Amazon. And we again have the same security options, but with Amazon, they typically require also an Mqtt client authentication, so that every client that is sending data to the Mqtt broker in Amazon is identified with an SSL certificate. And we checked it out and it works. Another thing we heard from Amazon is that you can actually parallelize the Mqtt connections if you need faster throughput to cloud. You can just open a lot of connections and get more data going in. This is something that we haven't tried out yet, but and we probably need to modify the SDK to have some parameters to define how many connections you wanna enable and how do you pull that. But that's something we learned just recently. And the third demo that we'll be working on together with the Aalto University and Shanghai Jiatong University in China is to study how could you do a globally distributed production. And here the idea is that we have a communication going between Finland and China. And the production system model here in Finland is based on an open source IEC 64099 PLC runtime. It's the Fordiac Forte that is actually running on Windows. You can run that on different platforms, and this is an open source implementation. So you can also get that and try it out yourself if you wish. We created there a simple model, or our friends in Aalto University created this model with the 4099 programming language or function block. And then they created a device gateway that can communicate with the runtime within 64099 XML format, and then publishes this data using UDP UADP OPC UA connection. And we have another component called the Edge Gateway here that subscribes to this UDP data. And at the same time, we also introduced OPC UA servers for both of these components so that we can connect with the traditional client to see what's in there. And on top of that, we finally go towards China by publishing data through an Mqtt broker that is then subscribed in China, where they are running an assembly line. And from the assembly line, they are sending their own Mqtt JSON back to us that we can use. And if we look at a little bit closer to the information models that are being used, so in this function block, we have, for example, the variable for the luggage position, X and Y coordinates. And on these gateways, we had the OPC UA servers. And if we connect to the device gateway, we will be able to see the value with the client server model, and we find it from the resources. And the idea here was that in the edge gateway, we also remodel the information. So in the device gateway, it was modeled according to a special information model that was a proposal for 61499 by the Aalto University. And on the edge gateway level, we show the same information modeled with the standard process automation device information model. And now actually then when we're publishing the information to China, we can send dataset messages that contain the same value in an Mqtt JSON or JSON payload. And this is now not the non-reversible, this is a reversible format, so it also contains a little bit more header information that the specific subscriber could use to filter out just the information that they want. But I think there is still like open questions that how should the data be named here in these JSON messages. We could use just take the device and plug its position and analog signal, but there's no standard actually how to map the OPC UA information models to these dataset messages on that level. So that is something that is a little bit missing, but you can do it on your own ways. But to conclude, still say that the OPC UA client-server model is still very useful and required for synchronous operations and for reading out information models. But the publisher-subscriber model will enable new application scenarios, improve scalability towards smart manufacturing networks, improve performance in local networks towards field exchange, for example, as we noticed. And it enables connectionless data delivery, especially in the edge-to-cloud scenario. There are tricky issues with PubSub, especially the configuration. I didn't really touch that. Didn't really have time to go deep in that. But if you have a large network and you have to configure every publisher and subscriber, what they actually publish and subscribe, that's not so simple. And the security configuration, especially in the UDP Ethernet APL case, is also a little bit tricky to configure. And for those purposes, we really would need some centralized management tools. So that's my presentation, and I think there are probably a couple of questions here.